In the framework of hypothesis testing, it's important for us to not only be able to run hypothesis tests, but also for us to understand what's actually going on with these hypothesis tests. What should we be expecting to see when we run these hypothesis tests? What might go wrong with them? What are the probabilities of us making different types of errors? It's also important for us to understand what's the probability that something is going to go right. If we're actually going to be performing hypothesis tests, we're hoping that these are going to be tests that are useful for us to learn about the world around us, for us to do science in some way. And one of the key values that is going to be useful for us to be able to compute in order to assess the utility of a hypothesis test is the power of a hypothesis test. So the power of a statistical test is a critical measure of its performance. If we're thinking about z-tests or t-tests, the power can be computed using a specified alternative hypothesis, and from here, we need to be doing normal or t-based probability calculations. So what are we talking about with the power and with specific alternatives? The power of a hypothesis test is the probability that we observe a true positive result. So that is to say, it's the probability that the null hypothesis is rejected, supposing that the null hypothesis is actually false. Right? So if we reject the null hypothesis, we say we have a positive result, and we want to know, well, what is the probability that we observe a positive result when that was what we were supposed to observe? What is the probability that we actually detect a positive result given the true value of the parameter? Okay. We denote this probability with the term 1 minus beta, where beta is the probability that a type 2 error is made. So a type 2 error has us making a false negative, right? So 1 minus beta gives us a true positive. So in order to compute the power of a hypothesis, we need to be able to directly compute probabilities when the null hypothesis is false. And in order to determine when is the null hypothesis false, we actually need to be a little bit more cautious with the alternative that we're thinking about, right? Because we'll need to be able to determine, well, what's the probability that we reject the null hypothesis if it's false? And so how do we specify this false hypothesis? Okay. So if we can answer, well, what is the distribution of the test statistic when the null hypothesis is false, then we'll know the sampling distribution that we should work with. And from that sampling distribution, we can calculate the relevant probabilities. Okay. In order to determine this, however, we need a specific alternative hypothesis. Because if you imagine a standard null hypothesis, we might write that our null hypothesis is something like, say, the null hypothesis is that the mean is equal to 0 versus the alternative that the mean is not equal to 0. When we need the null distribution, what we do is we say, okay, we'll take the value of mu equals 0, and then we can work out the distribution from there. But how do we take the value of mu not equal 0? What value should we take as the value for mu? And so because this is not sort of a concrete value, we can't actually work out a specific sampling distribution using this as the alternative that we're thinking about. And so instead, we need to be thinking about more concrete, more specific alternative hypotheses. Okay? So rather than us testing theta is equal to theta naught versus the two-sided alternative, instead we're going to consider these weird-looking hypothesis tests where theta is equal to theta naught versus the alternative of theta equaling theta 1. Okay? In this context, we can say that either theta is going to be theta naught or it's going to be theta 1. Right? So we are saying in some sense that if the null is not true, then we know that theta equals theta 1. In practice, these aren't going to be the hypothesis tests that we're really running, but the idea is that if you're willing to specify this value, right, then we can say, well, if it turns out that the null hypothesis is false and that theta really is equal to theta 1, what is the power in this situation? Okay, and so it's going to allow us to explore the power given some specified alternative. Okay, so if the null hypothesis is false, then we can say theta is specifically equal to theta 1. Theta 1 is the true value. And then we can say, well, what's the probability that we reject the null hypothesis if theta 1 is the correct value? Okay. If the null hypothesis is false, then theta hat is going to have the known distribution. And specifically, you could think about it as being the null distribution if you were testing theta equals theta 1. It's going to be the exact same distribution, right? And so however you would have to work out the null distribution, we can do the same thing to work out the alternative. And then we can use that to calculate our power. Okay. The same basic idea is going to hold for testing a single-sided test, right? Where again, we're going to need to take a very concrete alternative. So you would take some value that is less than or some value that is greater than the critical value, depending on it. So with that, if we have the test that we're actually going to be running and we have our specific alternative, how do we actually go about calculating the power? Now, given a test statistic, a specific alternative, and the relevant sampling distribution, it's going to ultimately be a probability calculation from that sampling distribution. So we must ask ourselves, well, what value of the test statistic would the null hypothesis be rejected for? Right, so what is the actual value that we could observe that if that had been what we had observed for our test statistic, we would have rejected the null hypothesis? Okay. This is oftentimes going to be the easiest to determine using critical values rather than directly from the p-values, for instance, although it's possible to do this from p-values as well. Tends to be just a little bit easier using critical values. So we can work out what would have been required to be seen in order for us to reject the null hypothesis. And then once we actually isolate back for the test statistic, then we can calculate the probability of observing that under the actual alternative hypothesis, right? So once we know the values that correspond to the null rejection, the rejection of the null hypothesis, we can solve for the probability of observing that event under the correct sampling distribution. If the sampling distribution follows a normal or t-distribution, then it becomes a standard probability calculation, where we will standardize that statistic and then use either the normal or the t-distribution to calculate the relevant probability. So let's actually take a look at this using our z-test. So suppose we are testing the null hypothesis that theta is equal to theta naught, right? And we're testing this against the alternative that theta is equal to theta 1. Okay. Under the null hypothesis, we know that theta hat follows this normal distribution, and here we're just going to use the notation the variance of theta hat, okay? Because this is going to hold for any statistic that follows the normal distribution in this way here. Okay. In this case, we can use a z-test, and from our z-test, we're going to be able to work out our power. So we're going to typically reject the null hypothesis if we observe our test statistic is less than z alpha over 2, or if it's greater than z of 1 minus alpha over 2, that two-tailed rejection. And our test statistic is going to be theta minus the value under the null divided by the standard error. And remember, the standard error here is going to be the square root of the variance, right? So we have that the standard error of theta hat is equal to the square root of the variance of theta hat. Okay? And so that's what our standard error is defined as. So we're rejecting it if we observe something that is larger in magnitude than our critical values here. So if we actually rearrange these equations here, okay, then what we can actually do is work out, well, what does that actually tell us, right? And so we'll take a look at just the first equation. So we want z to be less than or equal to z alpha over 2. And z here is going to be theta hat minus theta naught divided by the standard error of theta hat, right, which we want to be less than or equal to z alpha over 2. We want to try to isolate this for theta hat because that is our random quantity here, right? And so what this is going to tell us is that if we, say, take theta hat minus theta 0, by multiplying by our standard error, we get z alpha over 2 times by the standard error. Okay, and now we can add the theta naught to the other side. So we have theta hat is less than or equal to z alpha over 2 standard error of theta hat plus theta 0. Okay, and so that's going to give us this first bound that we are looking at here. Doing a similar process gives us our other bound. And so what we're saying is that if we observe theta hat that is less than this value right here, then we are going to reject the null hypothesis. Alternatively, if we observe theta hat that is greater than this value here, then we're also going to be rejecting the null hypothesis. And so then our question is going to become, okay, well, what is the probability that we observe either of these two inequalities here, right? So either theta hat less than this or theta hat greater than this, if the alternative is actually true, if the null hypothesis is false. And so to work out this probability, we're going to have to turn towards probability calculations, right? So if the null hypothesis is actually false, then theta hat is going to be distributed as theta 1 variance of theta hat, right? Where if we can sort of take the null distribution here, where instead of theta equaling theta 0, we take theta equals to theta 1. And so all we have to do is we change out this theta naught here for a theta 1, and the distribution will otherwise remain the same. Now, once you have the distribution there, we can actually work through the probability calculation. So there's sort of a lot going on here, but we can take this step by step. So to begin, we're thinking about 1 minus beta is equal to our power, right? And in order to think about our power, we know that we need the probability that this event happens or this event happens, right? And so we take, well, the probability that theta hat is less than the bound here plus the probability that theta hat is greater than the bound here, okay? This first bound, I will point out, is missing a term in it, right? So if we're actually taking this first bound, we should have plus theta hat 0. So with that typo fixed here, then we can consider, okay, well, how do we actually work out this probability? And we know that theta hat is going to follow a normal distribution under the null hypothesis, or under the alternative hypothesis, rather. And so what we can do is calculate our standardized normal probabilities. So we subtract off the mean, which in this case is theta 1, if the alternative is true, divide by the standard error. We do the same thing to the other side of the inequality here, so we're subtracting off the mean, dividing by the standard error. In the second probability term, we're doing exactly the same thing. We subtract off the mean, divide by the standard error. We subtract off the mean, divide by the standard error. Right? Once we're here, well, then we know that this term on the left-hand side here is going to be a standard normal. Same thing with this. And so these ultimately become normal-based probabilities, and we can express this in terms of phi. So it's going to be phi of our left-hand side here, or of the right-hand side, sorry, plus 1 minus phi of the right-hand side. And in order to simplify down, all we're noting is that in this case, given the setup that we have here, the standard errors can cancel each other out. And so that's how we get there. And ultimately, what we're going to say is that the power here can then be calculated as the summation of two different normal probabilities. What about if we're running a t-test instead? The setup's going to be much the same, but our distribution is going to change. So if we're testing theta equals theta 0 versus theta equals theta 1, the null hypothesis is that it follows a normal distribution, but we don't know what the variance is, then instead we're probably going to be making use of a t-test. Right? So typically we're going to reject the null hypothesis if the t-value is less than the lower critical value or greater than the upper critical value, and that t-statistic looks exactly like our z-score, except here, instead of using the true standard deviation, we're using the approximated standard error, the estimated standard error. Okay. If we rearrange this, we get similar bounds, right? So theta hat being less than or equal to the critical value times the standard error plus theta 0, theta hat less or greater than or equal to the same thing, right? With the opposite critical value. If the null hypothesis is false, then under the alternative hypothesis, then we have the same distribution, but again, the variance here is not going to be known. And so instead, we're going to rely on our estimated standard error, right? And so if we do this, we can work through our power calculations again. And again, we'll go step by step through this. So the power, which is 1 minus beta, is going to be the probability that this event or this event occur, right? So the probability that theta hat is less than the first term or that theta hat is greater than the second term. Okay. Now, in order to actually calculate out these probabilities, we want to get to our known distribution. And so we standardize the procedure here, but because we don't know the variance, we're standardizing on the basis of the estimated standard error, right? So we subtract off the mean, divide by the estimated standard error. We subtract off the mean, divide by the estimated standard error. Same thing in the second term. Right? And now what we have is that these terms here on the left-hand side and here on the left-hand side, these are going to follow our t distribution with n-1 degrees of freedom. And so if we take f here to be the cumulative distribution function for the t distribution with an n-1 degrees of freedom, right? So if we sort of just write that in, say down here, f is going to be CDF of t n-1, right? Then we get a very similar looking probability expression where we take what we had on the right-hand side and 1 minus what we have on the right-hand side. But otherwise, the math is sort of equivalent. And so with all of that, right, if we are doing a t-test or we're doing a z-test, then by identifying a specific alternative and by identifying the distribution under the alternative hypothesis, we can work through our standardization process, calculate either the normal-based probability or the t-based probability that gives us the power of a test. Now, there are specific results that are useful to see for our means and our proportions. They're going to follow the general trends that we just set out, but if we're testing a mean, we're either probably using a z-test or a t-test. If we're testing a proportion, we're probably using a z-test, and as a result, it's useful to see the power calculations for these tests in this specific way. And so if we're testing our mean and we know what the variance is, right? So we're using a known variance, we test h naught mu equals mu naught, versus the alternative of mu is equal to mu1, then the power is going to be given by this exact expression here. So we take phi of our lower critical value plus the difference over the standard error, and then 1 minus phi of our upper standard or critical value plus the difference over the standard error. Right? And so it's the same format from the last slide, except here we know that we're specifically testing about means. Similarly, if we're testing about means, but we have an unknown variance, right, then we're going to be looking at exactly the same procedure, except we trade out phi for f, where f is going to be the CDF of our t n-1 distribution, right? Our critical values become the t critical values here, and then instead of using a sigma, we're going to be using our sample standard deviation. Okay, and so in this case, we're going to be thinking about the exact same type of procedure. Once again, this is the result that we saw on the previous slide. If we want to test proportions and we're looking for a z-test for the proportion, so we know that we have a large enough n, right, then we can test proportions using the z-test. Now this is going to look a little bit different, and the reason it's going to look a little bit different is because we have this extra piece hanging out in the numerator here, right? So otherwise it looks quite similar, but we have this extra piece hanging out in the numerator. And the reason for that is because when we're testing proportions, we're actually in a situation where the standard error depends on the parameter value. So the standard error is going to be different under the null versus the alternative. And so because of that, we don't get the same simplification that we had before. But this is going to be much the same, right? We're going to take that the power is going to be phi of the first term plus 1 minus phi of the second term, right? Very similar to what's up here. We just have to be careful to include the fact that the standard error changes, right? And so each one of these is going to give us the ability to calculate power for the given settings that we're most interested in. So it's worth taking a look at how this actually goes. In our first example here, we have a marine biologist studying the average length for a specific species of fish in some particular region. Now it's known that this fish in other regions has a mean length of 25. The biologist collects a random sample of 36 fish from the region, finds that the sample mean length is 27 with a standard deviation of 3 centimeters. Going to run the test at alpha equals 0.05. We want to know what is the test's power, assuming that the true length of fish in this region is 26.5. So if it turns out that there's actually 26.5 centimeters for fish in this region, right, what is the probability that the null hypothesis is rejected, where the null hypothesis in this case is going to be that h naught mu is equal to 25. Right? And so normally we would want to be testing versus the alternative of mu not equals 25. But here we're saying, well, what if it turns out that the alternative we're actually considering is that mu is equal to 26.5? 26.5. How likely is it that if it turns out the truth is 26.5, we are going to reject the null hypothesis? Okay. And so the important thing to note here is that we have our standard deviation of S equals 3. Okay. And so we're running a t-test here. And because we're running a t-test here, we want to take the power formula for the t-test for our sample mean. Okay. So we can actually start filling in some of these values here then. All right, so we're testing mu is equal to 25 versus the alternative, the specific alternative of mu is equal to 26.5. The population variance is unknown, and so we're using a t-test, and we have the information that we've highlighted here, right? So we have our sample size is 36, the sample standard deviation is 3, alpha is 0.05, the null value is 25, the alternative value is 26.5. And so if we plug into our power formula here, right, we get 1 minus beta is equal to F. We need these critical values, and then plus the difference here, so 25 minus 26.5 divided by our estimated standard error. Same thing here, right? Our critical value, the difference over the standard error. And if we actually plug in n and alpha, right, we're going to need the critical value for T35, 0.025, and then we need the upper tail critical value for the same thing, right? And so expressed in this way, this is sort of a mathematical expression that's going to give us the specific power. If we actually want to work out what that is, then we're going to need to turn towards statistical software, right? So we have the same expression for the power here. How can we calculate that? We could use R, for instance, and to get this from R, we need to look at sort of an equation that is slightly longer than what we're normally looking at in terms of R code, but each piece of this we can work out, right? So the first thing that we need is we need this T critical value. QT is always going to give us the critical values from the T distribution, so we're looking for the 0.025 critical value with 35 degrees of freedom, right? And so that is going to give us the critical value here. We subtract off 3 from that critical value, and then we need to take f of that. In order to take f here, we use the PT function, right? So it's the probability from the T distribution. Once again, we're looking at 35 degrees of freedom. So we take the probability of the critical value minus 3, and then we take the same thing over on the other term here, right? So we have our critical value here of 0.975 with degrees of freedom equals 35. We subtract off 3 from that. We need PT of that, and 1 minus that corresponds to this full term here, okay? And so that is sort of a little bit more, but we're combining just the QT and the PT function as required to calculate out this term. And if we do that, what we find is that the power of this test is 0.830 and change, right? So what we're saying here is that if it turns out that the average length is actually 26.5, there's an 83.1% chance we reject the null hypothesis. Now, is that going to be powerful enough? That's really going to depend on the context here, right? Does that seem like it's going to be powerful enough for the researcher in this case? Depends on what the researcher expects to find, right? If they expect this and they really think it's super important, maybe 83% chance isn't high enough and they'd really like a larger power. And then if they want a larger power, they're going to have to consider what decisions can they make to get there. Okay. Now, it's important to take a quick look and see, well, what if instead of this being the sample standard deviation being 3, what if instead it had been the population standard deviation? Okay, so we can work through the same example again, but this time assuming that the population standard deviation is equal to 3. Otherwise, all of the numbers are exactly the same. So we're going to be testing the same null and alternative hypothesis, mu equals 25 versus mu equals 26.5. The population variance is known in this case, or it's assumed to be known, and so we're using a z-test. We still know sample size is 36, sigma is 3, alpha is 0.05. The null value is 25, the alternative value is 26.5, and so we can turn towards our power calculation. Once again, we're plugging into the formula, right? So we're taking our z critical values plus the same difference that we're looking at, our z critical value plus the same difference we were looking at before, right? This works out to be phi of the critical value minus 3 plus 1 minus 5 critical value minus 3. And so once again, if we actually want to get a number out of this, we can turn towards R. In order to do this, we're going to be looking at much the same thing, except now to get our critical value of 0.025, right, we need our Q norm function. Q norm gives us the critical values from the normal. So Q norm 0.025 minus 3, and then we plug that into P norm. Plus 1 minus Q norm 0.975 gives us our critical value minus 3. We plug that into P norm for the phi. And if we actually do this calculation in R, we get about an 85% chance. Okay, and so the power is slightly higher in the case of the standard deviation being the population standard deviation rather than the sample standard deviation. And that's to be expected. Anytime that you're making the assumption of a z-test, then if that assumption is true, you should have slightly more power. If that's not a true assumption, then we're into a weird situation that we sort of need to work out in its own regard. So we've seen that whether you're running a z-test or a t-test, that's going to influence the power, but it's worth thinking about, well, what are the other factors that actually influence power? There's going to be several factors that are influencing them, and some of these are going to be in our control, some of them aren't going to be. So the first one, and sort of a major factor, is going to be what is the actual difference between the null value and the true value, or the alternative. If you have a larger difference, that's going to increase the power. Now, importantly, whenever we're thinking about theta 1 here, right, whenever we're thinking about this actual value, right, what we're really thinking about is theta 1 should be the truth, right? And so theta 1 is the truth, and then whatever the truth actually is, right? So theta 1 is truth. Whatever the truth is going to tell us the relevant power for us. And so it doesn't work to just take theta 1 to be further from theta 0, right? Because that's only going to be believable if you actually think that theta 1 is the value that you actually care about. Okay? And so if the true value turns out to be very far from the null value, you're going to end up with higher power just because it turns out that the truth is far from what the null is, right? But we don't sort of control that. There's also going to be the level of significance. If you take a higher level of significance, so if alpha is increased, then that's also going to increase the power, right? So if you take alpha as 0.1 rather than 0.05, you're going to end up with a higher power. Now, of course, with alpha, we're also thinking about balancing the probability of a type 1 error. And so we need to be balancing how much do we care about the power, how much do we care about type 1 errors. And if you increase alpha, you're going to get higher power, but you're going to get a higher probability of making a type 1 error as well. We also can look at the standard error of the estimator. If your estimator has a smaller standard error, that's going to typically increase the power of the test. And so less variability is going to lead to more power. More variability is going to lead to less power. Now, if we're thinking through, well, what's in our control and what's not, the differences between values, as we were discussing, is not really in our control. The level of significance should be selected to balance out our power and our type 1 errors, right? And so we can't sort of directly control that necessarily. And the standard error is also not directly in our control. And so sort of what good is this if we can't directly control these things, or at least we can't specifically control them just to increase our power? The important thing for us to notice is that the standard error is typically going to depend on our sample size, right? The larger your sample size, the smaller the standard error for most of the statistics that you're going to be working with. And as a result, if you increase your sample size, you're also going to increase your power almost all the time. Okay? Higher sample sizes lead to higher powers. And so one of the controls that you have as a researcher is choosing larger sample sizes in order to achieve larger power. So how can we compare power with sample sizing? If you have a fixed hypothesis, some set level of significance, then we can very often use power in order to determine the necessary sample size. So the idea is that you can set out some power that you want to achieve. So I want to achieve 90% power or 85% power or 95% power, right? Whatever that power that you want to achieve is, you can set this out and then you can calculate how large of a sample do I need to take in order to actually achieve that power. Now with the z-test, it's the most common test that we're going to be applying this for. We can approximate the power through this expression here. This isn't going to give us an exact expression. However, this expression is going to make it a lot easier for us to work out, well, what is the actual power? Okay? And so this expression is going to sort of work no matter what, and it will be close to the true power. And so if we're working from here, then what we can say is if we specify our value for beta, right? So if we specify what our power should be, and if we know our value for alpha, then we can work out this critical value. And if we have our set hypotheses, right, then we know these values here. Okay, sigma is assumed to be known, or at least estimated in our sample, and all that leaves us to solve for is the square root of n here. Okay, and that's going to give us our sample size. And so we can actually work this out. If you solve this equation, then what you should find is that we get that n is equal to the inverse of our phi function minus our critical value multiplied by our sort of inverted or reciprocated expression in here. Okay, and it turns out that the inverse of our phi function is actually just another critical value. And so ultimately what we can say then is that n is going to be approximately equal to this to achieve our set power, right? So we want to take our standard deviation, multiply it by the difference in these critical values, divide by the difference in the values under the null and alternative, and then square it. Okay, and if you follow this formula, that's going to give you a lower bound on our sample size. And so if you compute this for plausible alternatives, then you can determine how many samples your study would actually need in order to achieve some set power. Now, if you don't do this, if you do not actually calculate how many samples do I need to achieve a power, then you might result in an underpowered study. Right? If you have an underpowered study, then that's going to make actual true results difficult to detect. Okay? And so it's really important to make sure that your study is sufficiently powered. If it's not, you're going to run into big problems trying to put it into practice. And so it's always worth doing this calculation if you're actually planning a study, because it might turn out that you're not going to be able to detect anything useful with your sample sizes, and that might sort of force you to go back to the drawing board and think about, well, what should I actually do? How many individuals should I actually take in here? There are going to be similar techniques for other tests. Oftentimes, if you're working for a non-Z test here, then it's going to require a lot more computation. So it's not going to be as simple as a formula. This is going to give you a very good rough sense for Z testing, but in more complex scenarios, you're going to want to turn to sort of more powerful techniques for power calculation. But all of them have a similar type of flavor where you can work out, well, what sample size would I need? Because that's the one thing that is fully in my control here. Okay. There are some other considerations we should make for power calculations. Okay, so the power is going to be a measure of how likely we are to find true positives. So if a study has insufficient power, then there's effectively no point in running the study, right? Because if there's not enough probability that we're going to find a true positive, right, then why are we actually conducting the study? If you think about, well, there's only a 20% chance that we find a true positive in this study, then that's a very ineffective use of resources to go about running that study. So the power is going to be critical for running our study here. Now, in this case, if you have a very underpowered study and you don't find a result, then it's hard to know, is that because there actually was no result, or is that because there was just a very low chance that we were actually going to find it? Okay. Now, the other thing is the power, the way that we have it set up, requires a specific alternative in order to compute. This can be seen as a limitation of calculating power in a sense, because what if you don't have a specific alternative? And so the problem is going to come up is if you specify an alternative and that's not actually the true alternative, then the power is not going to give you the true power. And so what some individuals do instead is they consider what we call a power curve. And essentially they calculate the power for a whole bunch of different values of the alternative. And then they look at how does that behave. And if you're looking at all of those values, then you can make a holistic assessment of, is there enough power? Is there not enough power? And what you'll find is that the power is going to get very small when you get very close to the null hypothesis value, and it's going to get very large when you get far away from it. And so what you're going to think about is over the range of plausible values there, over the range of values you actually want to be able to detect, what is the power like? And you can sort of run this same type of calculation for many different alternatives. Okay. It can also be explicitly useful to consider the trade-off between power and the level of significance, right? And so what we're thinking about here is now that we can actually calculate the power, we can think about the level of significance tells us the probability of making a type 1 error. So we have our probability there. The power tells us the probability that we find a true positive. Okay, and so we have probabilities for both of those. We want power to be as high as possible. We want type 1 errors to be as unlikely as possible, right? But we're trading these two things off. And so if you can actually come out and make probability statements about them, I want a power of at least 85%, and I want there to be a less than 1% chance that I make a false positive. Right? Then we are specifying alpha should be 1%. We need to solve for what our power could be to get it up to 85%, or whatever the numbers that happen to work there, right? So you can actually use these calculations very explicitly rather than just thinking, this is a study that I want high power, this is a study that I want a very low type 1 error rate. So the power of a hypothesis test is going to be a very important feature for determining the utility of the test. If you have too low of a power, the test isn't going to be useful. If you have a very high power, it's going to be a far more useful test. If we want to calculate the power under specific alternatives, then we can do this using our standard probability tools. If we do this for several different alternative values, then we're going to start to get a really good picture of how good is this test performing in the setup that we care about here. Is this worth doing? We can use this to inform sample size considerations, right? But the power is something we should always take into account when we're looking at a test. If we're underpowered, we should probably rethink distributing our resources elsewhere. But if there's sufficient power, then we're going to be really confident when we run the test that if we're finding a result, then it's probably a true result, supposing we have our alpha and our power balanced out very nicely.